So welcome everybody. The inspiration for this talk actually got at the Erlang user conference last year when Simon Peyton-Jones decided to talk about the Haskell core language, and I realized that perhaps there are a lot of people in the Erlang community who actually don't know a lot about what the compiler is doing inside, because Erlang has its own core language and so on. It's the sort of thing that if you're working with it for a couple of decades, you kind of forget that not everybody else knows this. So I thought it could be a good idea to give a talk about these things. And so I'm not trying to direct this at any particular level of expertise. It's for anybody who's either curious about what's going on or who's really into compilers and wants to know all the strange little details. I don't think I'll have time to go into too many details, though. It's quite a lot. So, what does a compiler do while you're fencing? Well, once upon a time, compilers were fairly straightforward things. They'd read an ASCII file, and they'll parse it, and at the same time spit out target code as assembly operations, which were encoded as machine code bytes. And those were loaded onto the computer, and we would execute them. Simple. But of course, there are complications in a modern world. Input isn't necessarily ASCII or the old days EBCDIC. So you have to decode whatever input you have, if you have Latin 1 or UTF-8 or Shift JIS if you're in Japan or something. So you get some abstract characters that you can work with on your language level. And of course, the result shouldn't just be a sequence of raw machine code bytes. You probably want a linkable or executable file, something like an exe file or an ELF file or something like that. And of course, the code that you generated wasn't that good. It needs cleaning up, so you have to add an optimization step there. And in order to do that, you have to represent these instructions internally in some way that's good for the stuff that you want to do with it. So you invent an intermediate machine code on which you work for a while to do the optimizations, and then you generate the target code. And then you realize that perhaps it would be a good idea to actually identify what's a string and what's a name and what's a number and so on before you start the whole parsing and code generation loop. So you tokenize, so you turn your characters into a stream of tokens, of symbols saying, okay, this was the integer 42, it's not the characters 4 and the characters 2, and so on. And then you might think that you want some macros and conditional compilation. And if you're in the C and C++ world, for instance, or in Erlang, you'd insert a preprocessing step on the token level before you do the parsing, which can handle include files for you, expand macros, do conditional compilation. And then you probably realize that it would be nice to separate the parsing from the code generation. Now that's not something that they wanted really to do in the old days, because computers didn't have a heck of a lot of memory. If you only have 100K or something to work with, you could easily run out of memory just trying to compile a large program if you tried to put that whole program in memory at the same time. These days, that's not an issue. So we separate the parsing step from the code generation, and we build a syntax tree that represents the code in a tree-like structure. And we use that to generate the code. In Erlang, we have an extra step between the parsing and the code generation, where a user can add hooks that do a parse transform to transform this syntax tree any way they like before it goes on to the code generation step. And the next thing to add is to simplify things for the code generation, for the code generator, by doing desugaring, which is you take the the full programming language and you try to rewrite it into simpler but equivalent constructs. So you remove all the syntactic sugar if you can, leaving only the primitives of the language. And that means that the code generation step will have to handle fewer constructs, and that means that there are fewer places that you can screw up as a compiler writer. And that's a good thing. It's much easier to prove equivalence on on the language, on the level of the language itself, than further down in the machine code level. Once you've desugared, you might want to actually do some optimizations on this level, since it's, as I said, easier to actually prove that you're still following the rules of the programming language. Once you move down into lower level code, it's harder to be sure that you've done the right thing. If you do a transformation on the level of the source language, then you can pretty much check the specification and see if these two things should be equivalent. So you add optimization both before and after the code generation. So that pretty much concludes the whole compiler chain from start to finish. And most compilers work in the same way, modulo details. For one thing, the choice of a core language, it could be that you just reduce it to a subset of your full language, but it's still that language, just a subset. Or it could be that it's actually a different language, but which expresses your source language in a nice way. So how does this apply to Erlang? Well, let's see the different ways of running the Erlang compiler. First of all, if you're working interactively in the shell, you can use the C shortcut. You just say C module name or file name and a bunch of options if you want. And that actually runs the slightly secret module C:C, which implements the shell shortcut functions. That in its turn compiles the file, and if it worked, it also loads the module. But how does it compile it? Well, it calls the API function for the Erlang compiler, which is the module compile. So it just calls compile file, gives it the file name and the options. Now what that does is that, well, it runs the whole compilation, and if it works, it returns OK under the name of the module that it compiled, and it spits out a bean file on the side. Now, this API doesn't actually load the module, so if you call it this way, then you have to load it manually afterwards. That's why this shortcut exists. And if you want to automate compilation through makefiles and other things, then you'd prefer to use the erlc command line tool, where you can pass flags like -d debug or -i.include. And you can add options like debug info and warn unused import, etc. So erlc is really just a small C programmer that's a wrapper which runs the real Erl emulator and passes on a couple of flags to say, run this module on this function and pass the rest of the options to it. And that module will check if there's a .erl extension, and in that case, call the regular compile file function. So it's just a simple wrapper making things easy for you. So if you have a plus option, that's passed verbatim as an option into the compile file call. But these shortcut options like -d and -i are massaged into a different plus option, because they're slightly hard to write. If you can write them as plus options with a bunch of quotes, etc., because they have to be complex Erlang terms. And the erlc wrapper is actually it can actually act as a front end for several different input formats. So if you have a YRL file, which is a grammar file for the YEC parser generator, it will detect this and it will call the YEC module instead to compile that grammar. Okay, so those are the different ways of calling the Erlang compiler. Now there's a specific option that you can pass to the compile file function, and that is the atom binary. And if you do that, the compiler will actually return a triple. Say, this was the name of the module I compiled, and here's the binary. So it won't save it to disk. It will return it to you as an Erlang binary object, a bunch of bytes, instead of writing it to disk. So the name of the option is binary, but this actually works for all levels of output. It just takes wherever it stopped and returns that to you. So if you say, compile this, but stop at the core level, and it will happily return the core code to you if you want to do some stuff with that. That can sometimes be useful. But the most useful usage of this is to pass the binary option and compile it completely to a beam binary, and then directly from your own code call the code loader and say load this binary as this module name, and say that this was the file path where I took it from. And then it will load it into memory. That means that you can actually compile stuff and load it without going to disk ever. That's useful when you generate code on the fly. So, of course, as I said, we don't really know what the encodings are. Erlang used to require that all input files were Latin 1, but that was changed a couple of years ago. So nowadays the default is UTF-8, and if you really want your input files to be something else than UTF-8, then you have to add an annotation to the top of the file. So the Erlang parser will actually, first of all, check if there's an annotation, and in that case, change the decoding to use that instead. So once it's gotten its stream of characters where you have forgotten what encoding they actually were in, then we can actually start doing tokenization. And in Erlang, the tokenizer is called erlscan. That's actually a fairly large-ish handwritten tokenizer, so it's not using the leaks tokenizer generator. If you want to look at it, it's kind of messy, but I think you probably don't want to try to switch to a leaks implemented version, considering the possibility of backwards compatibility going bad. Anyway, so this splits your character stream into a sequence of tokens. That's integers, floats, atoms, strings, keywords like case or end, operators like plus, separators like commas and parentheses. So it's actually you just get a list of tuples saying, okay, I saw an atom at line 1, and the atom was foo. And then I saw an integer at line 1, and the value was 42. And then I saw a case keyword, or an end keyword, or a larger than operator. So you see that these have a value, but these just are themselves. And there's also a specific token, which is called a dot token. It looks like this. And that's because Erlang code is separated into forms. Forms are snippets of code ended by a period plus white space. And that comes from its Prolog roots. And that's also used by the Erlang shell to know when the input of a complete statement is complete. And if you don't understand this, you will have a bad time when you try to work with the Erlang compiler internals. There's also some extra stuff that you can get from the tokenizer these days. You can ask it to return also the column number info and the original text of the token. You can ask it to insert extra tokens for you to examine, like tokens for every piece of white space or every comment. That can be useful if you're doing an IDE or of some kind. And these days you should also not match straight on these, because this thing, which usually means the line number, if you tell it to return optional information, then this will change to something else, and you shouldn't rely on that representation anymore. So you should use the new API functions, like erlscan column, to extract information from the token. That's pretty new stuff. So if you're a couple of major versions behind, all those API functions might not even exist yet. For some reason, the column number info still isn't standard, so you won't get column numbers in your error reports yet. Anyway, I hope that will change in the future. Okay, so we're done with tokenization. We have a stream of tokens. Then what happens is that the EPP, the Erlang preprocessor, kicks in. So that's a C-style token level preprocessor. Takes tokens in, gives more tokens out. It handles stuff like header files, include and include lib statements. It handles macro definitions and calls of macros, which look like this in your Erlang. Does conditional compilation, if-defs. It does the concatenation of adjacent strings, also something that C preprocessor does. And it does stringization of macro arguments, which is something that you rarely use, but it can be useful for debugging. So this runs on your token stream, and after that has happened, there are no includes or if-defs or defines or macro calls left in this token stream. All the code that was in include files is now part of the token stream. So include files are mainly used for declarations of like records, types, specs, etc. It's generally a bad idea to put functions in include files. It tends to screw things up sooner or later. You have but in order to track where your code in include files, etc., came from, there has been some new position declarations inserted. And these are something that you typically never see on the code level, on your source code level, because they happen down here. So the preprocessor will say that, okay, now I've entered foo.hrl. Now I've just left foo.hrl and gone back to line 17 of your original source code, etc., etc. So it tracks this way. I think that's also something that a typical C preprocessor would do. If you really want to see what your code looks like after preprocessing, actually a bit further down, because it does the parsing also. But if you want to inspect what's happened to your code after most of these preliminary things are done, you can pass the upper P option to the compiler, and then it will stop and output a .p file, which is really just a pre-printed source code dump of what your stuff looked like immediately after parsing. So if you're really lost when you're working with macros or something like that, then you can use this for debugging. The next step is the parser, Erl parse, and that's not handwritten. I think in the olden days it actually was, but since a long time back it's been implemented as a YEK grammar, and YEK is of course the Erlang implementation of the YAK parser generator. So that is called erlparse.yrl if you want to dig into it and see what it's doing. So it takes these tokens as input, parses whole forms at a time, and then returns a syntax tree which is known as the abstract format. This stuff is documented, but it's fairly messy to work with. So it looks something like this. Here's a representation of a function that's been parsed. So say that, okay, you have the function f at line 1. It takes one argument. It has a bunch of clauses. Actually, it just has one clause at line 1. So I think I've put the line 1 everywhere here for simplicity. The parameters of the function are the variable x. It's just one parameter. There's no guard, or there's an empty guard. And the body is a tuple consisting of the atom foo and an operation that says plus of the variable x and the integer 1. It's not rocket science, but it's also slightly hard to follow, which is why I, a long time ago, wrote a library called the syntax tools, which gives you a real abstract data type for syntax trees. So that's a superset that works on any abstract format syntax tree as input. And you can insert comments and user annotations on subtrees, print that out, and and if you're done with it, you can also revert it back to the plain abstract format for giving it back to the compiler to do some more work on it. And there are some utility functions for easy traversal, etc. In the syntax tools, there are some other things like a more flexible pretty printer. There's a thing called the EPP dodger, which is sometimes useful for if you want to parse a source file without actually expanding any of these preprocessor declarations. Then you can do that by a lot of trickery, but it can't handle too weird uses of macros. And there's also some stuff for digging out the original comments from the source code and inserting them into the parse tree. And that's what the edoc tool uses to gather your inline documentation and associate that with your functions. So that's all in syntax tools. Another part of that's a more recent addition is something called Merlin, which is a meta-programming extension that gives you quasi-quotes and meta-variables. So you can, once you include the Merl header file, which in its turn defines a couple of macros and runs a parse transform, then you can write things like q of the string that represents any Erlang expression. And what you'll get is an extended Erl syntax abstract syntax tree with whatever that variable was bound to in your environment automatically inserted. And you can even do matching and case switches. So you can take, if you got an AST that you got from somewhere, you can match on this pattern. And if it matches a two-tuple foo comma something, then you'll extract this into the variable x and get that subtree of the syntax tree. There's some other small things like a nice utility function for showing an outline of the syntax tree. So this stuff really simplifies when you want to generate code on the fly or maybe write a parse transform. So what are parse transforms? They're simple hooks. You declare them by saying, in your file perhaps, saying compile with the option parse transform and the name of a module. And that module acts as a callback. So the compiler will, after it's done its parsing, it will run the parse transform that you've written in your module, passing it the forms that it parsed, and the compiler options if you want to look at those. And then you can do whatever you want with this syntax tree, and then return it to the compiler, which will proceed with compilation. So you can do simple, straightforward things, or very, very weird and nasty things. Merl is sort of a middle ground. It's slightly weird and nasty. And you can have multiple transforms for single modules. There's nothing preventing that. Possibly if you get into some kind of ordering issue, but most parse transforms that I've seen are They don't really care about other possible transforms. Some examples are QLC queries, known as query list comprehensions for Manisha. If you use those in Erlang, that's a parse transform that changes what a list comprehension means if it looks in a specific way, and allows you to use that syntax to write compact and efficient Manisha queries. The eUnit library uses a parse transform for automatically export your test functions, so you don't have to declare those manually. Okay, so once the parsing and the parse transformations are done, there's something called erlint, a module called erlint that's executed, and that does all the checking of the code at the syntax tree level. It checks. That's what handles most of the compiler warnings and errors that you'll see. And if it returns any errors, then the compiler will stop. If it doesn't, then as far as the rest of the compiler is concerned, the code is good to go. If you want, you can add a -w error to the erlc command line to turn all warnings into errors if you want a completely warning-free build. Okay, so now we've entered the compiler proper. Then you get a pre-expansion step. So you probably know that Erlang's record syntax, not maps, but records, looking like this, is actually just an alias for plain tuples with a tag. And that's expanded away by this pre-expansion step. There are also some other things happening, like automatic functions generated. The module info functions are inserted. And if you had any import declarations, those functions are expanded to be fully qualified calls. So the rest of the compiler doesn't see any of these complications. The records are gone. They're just plain tuples. There are no imports. You may know that there's a debug info option in Erlang. So what that does is that it adds an extra chunk to the generated beam file called the abstract code chunk. That's just a dump of the abstract format syntax tree for the whole module at this point. And if you don't like your customers to see this data, but you still want to provide the debug information in case you want to go on site and debug stuff for them, or something like that, then you can encrypt this. One fun thing is that it's possible to extract this abstract code and recompile it to regenerate the beam file, because all the external dependencies like included files, macros, records, that's all expanded away. You can just give it back to the compiler and generate a new beam file, possibly after some fixes if you need. After this, we go into core Erlang. Now, core Erlang was inspired mainly by the standard ML language specification from '83, where they used a core set of concepts, meaning that the rest of the language just becomes syntactic sugar. You reduce your language down to the bare minimum and use this bare minimum. You specify what it means, and then you use this bare minimum to specify what the rest of the language means, because that's just sugar on top. If you've done this planning ahead, so that you started out with a core language and used that to define the rest of your language, you're safe. But if you have to retrofit the core language into an existing language, then you have some work to do. And that's what we did. So you really need to rediscover what are the core concepts of your language. Imagine that you try to pick up Fortran and create a core language for it. You'd have to do some serious thinking. What is the core here? So you need to figure out what are the core concepts and how do you map all the existing higher level constructs down to this core without losing any detail. And it may well be that some of that detail was not well specified to begin with, so you have to figure out what's the de facto implementation. For instance, we had to figure out what are exceptions really about in Erlang. How do they work? Not all of that was specified. And it took a while before we could come up with a design for the exception handling on the core level. So we did this work in about 90, I don't remember now, 97, 98, maybe a bit later. Somewhere thereabouts, core Erlang went into the Erlang compiler as a new step. Because working on the Erlang level is hard. As I said, it's nice to work on the level of the source language because it's more well specified than working down there in the grotty machine code. But Erlang has its peculiar syntax, which is quite good for writing programs. But for automatic manipulation of programs, it's much harder. There's pattern matching and there's clauses in many different constructs. There are pattern matching in function heads, funds, case expressions, if expressions, receive expressions, try expressions, and of course the equals match operator. And all those instances are slightly different. And if you rewrite one expression on the Erlang level to another, they might look equivalent at first, but they aren't necessarily completely equivalent. For instance, if you think that you might be able to rewrite an if into a case, but then you'll get slightly different exceptions if there's no match. So you just change the behavior of your program. And some people might think that's never mind, I get a slightly different error. But for some people that might break their test suites, so not funny. And Erlang's variable scope and bindings are, as I said, they're they're quite good for a programmer. But when you're trying to automatically rewrite and manipulate the code, these scope rules and bindings are very complicated to follow and maintain when you're rewriting stuff. Core Erlang, on the other hand, is simple. There are quite few constructs. Plain nested scopes, like in normal lambda calculus. All variables in patterns are considered new variables. You don't import them from the surrounding scopes. All this makes it much easier to manipulate and move things around on the core level. The only clauses are those in case and receive expressions, and I'll show you later why we kept the ones in receive. There's almost no syntactic sugar. There are few alternative ways of expressing things. Atoms, for example, are always single-quoted. There's no fancy list notation, so you can't write list 1, 2, 3 line rest. You have to say the console of 1 and the console of 2 and the console of 3 and rest. So writing that manually can be a bit of a bore. But this is meant for machine generation anyway, so it's more important to have it very simple and concise. You can have normal Erlang-style comments. Okay, so let's look at what are the constructs in core Erlang. There are variables. They can be plain variable names or function/arity. Makes it easier to track which things are exported and so on. There are literals, constant terms, like integers, floats, atoms. We do allow strings as syntactic sugar for lists of integers. And you can have lists and tuples of constant subterms. That's also a constant literal. And then you have consoles for building non-constant lists. There are tuples for tuple construction. There's support for binaries and bit strings on this level, and also recent addition maps. There's not been time to actually write up any documentation for how maps work on the core level. So I'm going to skip that. Then after those basics, there's funds, a function of a number of variables to a body. One peculiarity is that you have multi-value groups. So core Erlang works on multiple values. Any single expression E1 is actually the sequence of that value. There's explicit sequencing. You can say first evaluate this and then evaluate that. And there are let expressions. And here's where you see that you can use these multiple bindings. if you have an expression here that returns multiple values, you bind those multiple values to corresponding variables and use that in the body. There are no safety nets. So if you should screw up how many things are actually produced by this side and how many variables you bind on this side, you could end up with uninitialized variables and things like that. So that's one reason to not do things on the core level unless you're sure that that's what you want to do. So if you're just doing some simple transformations, generating code, then it's probably better to generate Erlang code because that'll be completely checked all the way. But if you're implementing your own ML, then this is the way to go. Then we have a letrec construct, which lets you define a number of functions that can be mutually recursive, or just immediately recursive, in a body. Now, normal Erlang doesn't let you do this. But you can do it on the core level, which means that you can have locally defined recursive functions that aren't visible somewhere else. And then there are modules. Now, a module in core Erlang is really a letrec. It's a bunch of possibly mutually recursive functions. And a keyword module, you name the module, you list which of these are exported. You can list a bunch of attributes, and that's it. That's a module. But of course, you need to be able to call functions. So there's a syntax for applying a function. Oh, sorry. It should say apply f. And this should say call mf. There's a keyword missing here. But for function application, that's actually the same for both local function calls and for any fun. There's no difference in core Erlang, just like there's no difference in lambda calculus. And if you want to do a remote call to another module, use this syntax. Then there's, for compiler intrinsics, that's the kind of special functions that you typically need when you implement something on the low level. You want to express that. You have basically the choice of expressing it as a call to a magic function with a magic name. Or you can say that these are special calls with a special namespace. And we went with a special namespace that makes it easier to know what you're doing. These aren't defined at all. That's completely dependent on what you're doing in your compiler, what intrinsics you come up with that you need. And then we have case switching. Simple case expression of clauses, where clauses they look like this. You have a number of patterns, so you can match multiple valued expression against multiple patterns, when guard, then body. And this allows us to have just one case expression, both for the kind of matching that Erlang does in function heads, where you have a number of arguments that you switch on, or that you have a case expression where you just have a single argument that you switch on. So all these can be expressed as core Erlang multi-valued case switches. And then we have receive expressions, and these also use clauses. Receive, a bunch of clauses for matching the incoming message. That's of course just one value. After timeout, do action end. So it looks very much like an Erlang receive. And finally, we have try, catch, and these are much more bare bone on the core Erlang level. They say, run this. If it works, take the resulting multi-valued and bind it to these variables and execute body. So if it works, it's just a let binding, really. If it doesn't work, then forget whatever it produced and you'll get some exception information in one or more variables that get bound to these variables here, and you enter the exception handler code instead. And exactly what these mean is also implementation dependent. So that's an implementation detail of the Beam compiler. The core language doesn't specify. So let's look at why did we keep receive with clauses instead of expanding it. Well, because receive is really a state machine. It's not a simple expression. You don't just pass through it. It's a state machine. So if you have a normal Erlang receive pattern when guard then body, etc., last pattern when guard then body, or otherwise after timeout do some action and we're done. Okay. What does that mean? Well, if we expand it to something equivalent that shows you what's happening, we can say that it does this. Let's reinterpret the receive keyword and say that really does just the initialization. It sets up the timer if needed. It sets up a message pointer to the mailbox and describes the head of the loop here. And then it picks out the first message, looks at that, doesn't remove it from the mailbox yet. So we've reinterpreted what the receive means. It doesn't remove it yet. Pick it out, then we do the case switching. Now I've separated the switching from the receive statement. This is always very simple to compile. And then I do a case switch over the message, and if one of the clauses is matched, then I insert a special primitive operation here before I do the body that says, okay, we had a match. Select this message, remove it from the mailbox. This is the one that we wanted. And then enter the body and drop any timers and etc. And if we didn't match any of the patterns, then we have a catch-all clause at the end, which does a next primop instead, which will leave the message in the mailbox and advance the pointer and go back to the loop head. So we could have decided to say on the core level that we wouldn't have any case expressions. We'd always expand it to this. But this isn't nice to work with. If you want to do some manipulations on the core level, this isn't what you want to see, because you can probably not do anything with this before you start to break what's going on in your receives. So this transformation actually happens much further down in the stack. Okay, so you can compile core code to Beam code by adding a from core option. It's possible that the erlc command will actually identify the .core here, so you don't have to specify from core. But if you're calling the API function, you have to say from core. So you can pick up an existing core file or syntax tree on the core level, pass it to the Beam compiler and say, okay, finish compiling this to Beam code. It's a good idea to add the clint option, not clint, I guess. Because then you'll get some safety checking if you've done some handwritten core code or generated core code, it does some safety checks. But it doesn't catch all possible problems, and if you've generated broken core code, that'll probably cause the compiler to fail somewhere further down. What's happening here, once you have core, well, the compiler does some things like constant propagation and constant folding, which is when you have something like a sequence of, say that x is 17, and then you say that y is x plus 4, and then you call f of y. Okay, but then we can propagate the value of this because that's a constant. That makes y equals 17 plus 4. But that's a constant expression, so we can fold that. So y just becomes 21. Great. So that happens at compile time. There's some extra stuff like type tracking for basic stuff like integers, booleans. There's no proper type analysis happening right now, but there could be. if somebody had time to implement it. There's also a neat little option that not many people know about. It's called inline list functions, list funcs. And that tells the compiler that whenever you have a call to lists map or something like that, it will actually inline the body of a typical map implementation in your code. So you won't actually make any call at runtime to the lists module. You'll just have a piece of code that does the looping for you in your own module. Now you can combine that with additional inlining. So if you say erlc plus inline, then the automatic inliner will kick in. And that uses a couple of size and effort parameters to decide on its own what to inline and what not to inline. It does a pretty good job of it. You may want to tune the parameters if you really rely on this. There's also some experimental support for unrolling, so you can say inline unroll up to level 3. So let's just quickly, what happens after this is that you're starting to go down to the beam level. And then to do that, they first transform into something called kernel Erlang, which is an unofficial intermediate format, could be changed or something in the future, so don't rely too much on it. But you can compile to kernel to inspect it, for instance. It's even simpler because it has no nested expressions, only unique variables. It differentiates between tail calls and normal calls. That's where the pattern matching clauses get compiled into decision trees. And lambda lifting happens, which is when funds are converted into top-level functions. So after this step, there are no funds. There are no letrec funds, nothing. There are only top-level functions, which may have extra parameters for the captured information. Before it goes into kernel Erlang, there's actually something cool called destructive setelement. So yes, there's destructive updates going on in your code. Do you know? If you use the record syntax and you update multiple elements of that record at the same time, then that will generate a sequence of set element operations. Sort of insert an element into element 3 of the tuple, then into element 5 of the tuple, then into element 7 of the tuple. And if you did this naively, each of those operations would copy the whole tuple to the next step, changing just one element. But I try. But this trick means that since the compiler knows that there can't be any if the compiler knows that there can't be any garbage collection happening, and this is all just the same tuple being updated again and again, then it can replace everything except the first operation with destructive operations that actually just insert a value into the existing tuple. So let's quickly describe the Beam abstract machine. It's a register machine. It's not a stack machine like JVM, similar to the old Prolog WAM machine, but it doesn't have unification or logical variables or something. Instead, it has what's known as X registers and Y registers. And X registers are registers. So they contain one word. Y registers are slots in the current stack frame. So Y1 is the first slot, etc. The Beam supports tail recursion, so there are different operations for making a non-tail call and a last call. A last call will discard the current stack frame before it jumps. That means that the stack doesn't ever grow. And it's also good to know that the Beam instructions are really a kind of a transport format. That pretty much what you can say about the JVM as well. The Erlang runtime system rewrites them when it loads them into more specialized internal operations, typically figuring out if some things occur very often together, then they can be bunched into a single operation, stuff like that. So in order to generate Beam code, there are some things that are happening. You get variable lifetime analysis and insert labels as target for jumps. You have to allocate X registers for different variables. You have to save those X registers in stack frames, that's Y registers, across function calls. Standard stuff, really. Function call parameters always use x1, x2, etc. And there's operation inserted for making space on the heap, which is also kind of different from how, say, a JVM works. So whenever an Erlang program needs to create a const cell or something, it just says, OK, I need 2 more words. Let's check if there's enough space. In that case, advance the memory pointer and do that. And if you have source line information from your original source code as annotations, then that's now inserted as dummy beam instructions, which later become moved into a table that maps operations to original source lines. There are some optimizations that happen down on the beam level. Typically, dead code elimination and unreachable code, peephole optimizations, pretty standard stuff, and some things that I don't have time to go through. After that, it's just a question of validating, doing some basic sanity checking, and then map the intermediate code for beam operations, which internally looks something like a move the atom foo to the X register 0. And that will be remapped to the actual on-disk encoding, like a byte 64 for that opcode, etc. There are currently about 150 different opcodes in the beam. And then the binary encoding is created with several different chunks. You get, of course, the bytecode itself, but also a table of all the atoms in your module, other constant literals, what attributes you had on the module, a table of all the entry points, your exported functions, the table that maps source line, object code to source lines, compilation information, debug information, and some other things. Okay. I hope that's you.